Okay, welcome back. You might be possibly amused to find that this is actually the second time that I'm recording this lecture because the file got corrupted the first time. So hopefully that means this will be smoother for you. It turns out I had too much stuff on my hard drive and the file was too big and it got corrupted, and so I have to re-record. Okay, so you should be listening to this in preparation for Thursday of week 13, and hopefully listening to this before the lecture period so that if you have questions, you can come to class at the regular time where a TA will be there to answer your questions. I assigned assignment 7 for the Tuesday lecture, and so for today I will just say, please keep working on your project. And the goal there is that if you do these last homework assignments of the semester, you will be well poised to turn in your project report without any stress at the end of the semester. So today I'm going to bridge from the content that we talked about for the Tuesday lecture into some topics related to deep learning because next week on Tuesday of Thanksgiving week, we will talk about, I'll walk you through an example of actually using deep learning in Weka and also give you kind of a researchy applied example of how we've used deep learning in my research group as an example. Okay, so we are bridging from what we had talked about last time regarding feature selection, and that's going to prepare us for thinking about concepts in deep learning. So let's look at this representation of a data set that you can see on your slide. These red pluses are data points. In this particular case, you see them in a two-dimensional space. Imagine then that these instances are represented with two different features, which we'll call X and Y. So you see the X and Y dimensions, they are labeled on this slide. But these are not the only features that could be used to represent this space of data points. The green axes would be able to represent them as well. And the green axis that's labeled as PCA1, you can see, is positioned along the part of the cloud of data points where it represents the greatest amount of variance, or kind of the biggest spread of our data. And the second one captures most of the rest of the positioning of, actually all really, considering that you're seeing these in two dimensions, of the position of these features, or sorry, not features, but instances. So you could consider PCA1 and PCA2 as dimensions that replace the original X and Y. Now, it could be, so we started out with 2 dimensions and we ended with 2 dimensions, but we could have started with any number of dimensions. The idea of a principal component analysis is that you're reducing down the dimensionality. Let's pop up a level. What are we doing here? We talked in the last lecture about feature selection. The idea of feature selection was we started with a large number of features and we selected a subset of them. But the features that we ended up with were still ones among the original ones that we started with. When we do a principal component analysis, we are similarly trying to get down to a smaller number of features. But the features that we end up with are actually different from the features we started with. They are created through a linear combination of the features we started with, and they're meant to redefine or define a new space in which those data points can be placed, where the instances will be placed in relation to one another similarly to how they were in the original space, but just in terms of different features. So what's happening is that when you do a principal component analysis, you progressively define features that can represent most of the remaining variance in the positioning of the instances within the original multi-dimensional space. So here, as I had said before, PCA1 is positioned along the cloud of instances where it indicates the dimension along which most of the spread of that cloud of data points is. And so you could say PCA1 represents most of the variance in the positioning of the original instances. And PCA2, which is perpendicular to that, is representing the rest. So in this particular case, since it was in 2 dimensions to begin with, we wouldn't need more than 2, but we could have had any number of original features. And so therefore, we probably would need more than 2 principal components to capture most of the variance in positioning within the original multidimensional space. We can decide how many of those we want. So we squash down any number of dimensions into any number of a smaller number of dimensions. And the attempt is to capture as most of the original variation in positioning as possible, but we'll probably lose some. But in the end, we have then the original dimensions and the new dimensions. And we can map from one set of dimensions into another set of dimensions. In this particular image that we see, it's pretty clear how you could represent each one of those red X's in terms of the original X and Y, or in terms of the new PCA1 and PCA2. And it's really the same idea, even if you had more in the original, and even if you had more than 2 in the PCA dimensions. The idea is that every data point can be represented within either one of these frames of references based on where it's positioned. And so then we should be able to compute a mapping between those 2. Okay, now there are other methods for doing similar mappings. So you may have heard of latent Dirichlet allocation. It is a probabilistic form of what we call topic modeling. In latent Dirichlet allocation, we are starting with the term by document matrix. You see that down in B below. So what we see is that in this particular representation, it's kind of on its side from what we would usually expect to see. Normally, we would consider that if we had a set of documents that are data points, each document would be a row, the set of words that are features would be columns, and then the values would be either binary if we had a unigram binary representation of the feature space, or counts. How many times does each word appear in each document? Here you can see it's on its side, so every document is a column. Now, from this representation, we can compute the probability of each word in each document based on, its frequency relative to the number of words that are in that document. So for every document, we have a distribution of word features. Okay, that's our original representation. So every document is represented in terms of the words that are in it. But if we wanted a reduced representation, we might want to represent a document in terms of which topics were represented and in what proportions. So we can construct a topic representation by decomposing this term by document matrix. And we can decompose it into 2 different matrices. In the LDA version, it's a probabilistic decomposition into a matrix that represents the probability distribution of words within topics, and another one that's the distribution of topics within documents. There's also a version that's similar to this, called latent semantic analysis, that does a similar kind of decomposition of 2 matrices from an original term by document matrix. This is a non-probabilistic transformation into 2 such matrices, where we then get latent dimensions. Again, these are like principal components in some sense. They are a reduced set of features in comparison to the word features. And what ends up happening is that then every one of these latent features is related to a vector of word values. And similarly, every document can be represented in terms of these latent features. So it's very analogous to the topic modeling case. So there are lots of different methods like this, where we start out with a very large number of very simple features like word features. And but it doesn't have to be words. They can be any kind of features. And within data points, there are relationships between these features, things that happen at the same time, often in the same instance. So like words that occur together within the same document, or maybe it's like kinds of metadata features that occur together. So let's say it's metadata for movies, and it might be, certain kinds of characteristics of movies that go together, like that it's a space movie and there are certain directors of space movies and they have a certain kind of budget that you expect, and they spend a certain amount of money on costuming, So there can be relationships between your basic features. And when you reduce down to a reduced representation, then it's helpful to find these relationships between your basic features, because if they occur together, then you can represent that they were all there with a reduced feature that represents the correlation between those things. So essentially that's at a very high level the kind of idea that's being captured. So where does that leave us? It leaves us with the idea that in contrast to feature selection in the way that we talked about it in the last lecture, another way of doing dimensionality reduction among our feature space is to re-represent our features so that each feature represents more than one feature, really. So we want to find a very compact representation of our feature space so that we can get the same amount of information, or almost all of that information, with a smaller number, more compact, more meaningful features. Now, let's go back to the probabilistic graphical model case, or the latent Dirichlet allocation case. These probabilistic topic models are the very simplest form of a kind of structured machine learning model that used to be very popular, called, as I said, probabilistic graphical models. And, in some sense, most of these probabilistic graphical models were, at least the ones that show up in my field of text mining and natural language processing, were sort of variants on latent Dirichlet allocation. And if you saw any of that work presented anywhere, you saw plate diagrams that were like what you see on this Wikipedia page. And if you're not a machine learning person, when you saw those, it might have been sort of mysterious to you. But today, I'm going to unpack that slightly for you. And I want to unpack it because I want to start to introduce you to the idea